goal of this lecture. Today I will discuss some question which had come in different type of competitive exam based on inner product. Because I have told you many times, inner product space actually very important for all competitive exam. Our first question which had come CSIR NET November 2020 exam. The question is basic question, but just for deep knowledge I have indicated this question again and again. Which of the following be inner product on vector space of all real valued continuous function on the closed interval 0, 1? Option 1. First option, inner product f with g equal to absolute value of integration 0 to 1 ft gt dt. Option 2. Inner product f with g equal to integration 0 to 1 absolute value of f of t gt dt. Option 3. Inner product f with g equal to f of 0 g0 plus f of 1 g1. Option 4. Inner product f with g equal to integration ft gt dt. At first recall the following properties. A function would be inner product when it satisfies the following property: u with v equal to v with u, that means this is symmetric property. And this satisfies the distributive property u plus w, inner product u plus w comma v equal to inner product u v plus w v. It satisfies the linear property alpha, inner product alpha u comma v equal to alpha times inner product u v. It satisfies the positive definite property inner product u with itself always greater than equal to 0, and this inner product u with itself equal to 0 when only if u equal to 0. For this, consider alpha equal to minus 1. Then inner product minus f comma g equal to modulus of integration 0 to 1 minus f of t gt dt, and this value is, since mod term, so this value would be just cancel minus from integration, then this value would be positive. That means inner product minus f comma g is equal to inner product f with g, but alpha with inner product fg equal to minus 1 absolute value of 0 integration 0 to 1 ft gt dt. This is not equal to inner product f with g. That means inner product minus f comma g not equal to minus inner product f comma g. So option 1 is a wrong option. Similarly, we can tell option 2 also wrong option. Similarly, by first similar to first option, we can take alpha equal to minus 1. Similarly, this would be wrong option. Option 3, notice inner product f with g equal to f of 0 g0 plus f of 1 g1. At first option 1 and option 2 is a wrong option. For option 3, we have to check inner product f with itself is greater than equal to 0. Notice here f comma f equal to inner product f with itself equal to, since f of 0 g0 plus f of 1 g1, that means this would be f of 0 plus f of 1 times f of 1. Just put the value, this value would be 0 plus f of 1 times f of 1 means just put the f of 1 means 1 minus 1, so this value also would be 0, that means this value is 0. Notice the condition when inner product u with itself is equal to 0, that means the value u is 0. But here I have considered non-zero continuous function in C01. But I have got f with itself is equal to 0. But if we consider f of 1 over 2, then this value would be 1 over 4, which is not equal to 0. That means I have got f with f equal to 0, but the function is non-zero function. Therefore, option 3 also wrong option, and only option 4 is a right option. Just check it itself. This is the standard inner product. We all of us know inner product f with g equal to integration 0 to 1 ft gt dt. This is the standard inner product. Our next example, let C01 be the space of continuous real valued function on 01, and inner product f with g equal to integration 0 to 1 ft gt whole square dt, where fg belongs to C01, then option 1 is this inner product. Option 2 imply this is bilinear from on C01 but not inner product. Option 3 imply this is not a bilinear from, and option 4 imply inner product f with itself is greater than equal to 0 for all f belongs to C01. Here the question about inner product and bilinear from. We all of us know bilinear from on a vector space V is a map which is satisfied if this is both linear in component wise. In inner product, this is we all of us know inner product alpha u comma v equal to alpha inner product uv. But bilinear means this is linear about this component, also this is linear about this component. Then this is the bilinear from. We all of us know this is. In my previous video I had discussed this topic elaborately. If you don't see my previous lecture, at first see the playlist, then you will understand the all part clearly. At first I will check, is it inner product? Because I have told you many times, inner product space. This is inner products. Which of the following be inner product or not inner product? For this type of question, check the positive definiteness at first. Integration 0 to 1 ft whole square dt. This is equal to integration 0 to 1 ft whole cube dt. If we consider ft equal to minus 1, then this value would be integration 0 to 1 minus 1 dt. This value would be minus 1. So I have got inner product f with itself is less than 0. Therefore, positive definite property has broken here. This is not be inner product. That means option 1 is a wrong option. And notice option 4 here has told about the positive definiteness property. This is also wrong option. Now I will check is it bilinear from? Since here the square term gt whole square, this is not be bilinear. We all of us know. Consider inner product f comma g plus h. This is equal to integration 0 to 1 ft g plus h t whole square, and this is equal to integration 0 to 1 ft g square dt plus integration 0 to 1 ft h square dt plus 2 integration 0 to 1 ft gt ht. Notice this is the extra term, so we cannot write inner product f comma g plus h as inner product f with g plus inner product f with h. So this is break the linear property, so this is not be bilinear from. Option 2 also wrong option, only option 3 is a right option. This is not be bilinear from. I hope my all viewers have understood. Okay, well. Next question, which of the following be bilinear from or inner product on MNR? Option 1 f of AB equal to trace of AB. Option 2 f of AB equal to trace of AB transpose. Option 3 f of AB equal to trace of BA transpose. Which of the following be inner product? For this, first f of AB equal to trace of AB. First I will check the bilinear from. F of AB equal to trace of AB. This is the first question. For this, at first I will check the linear property for bilinear term. Then f of alpha a plus b comma c by the defined, this is f of AB equal to trace of AB. That means this is equal to trace of alpha a plus b dotted with c, and this is equal to trace of alpha a plus alpha b dotted with c. This is equal to trace of alpha AC plus alpha BC. And since alpha be a scalar, so we can write this as alpha times, we all of us know trace of a plus b equal to trace of a plus trace of b, alpha times trace of AC plus alpha times trace of BC. And trace of AB equal to f of AB, so this is equal to alpha times f of AC plus alpha times f of BC. So notice here the linear property of first term has satisfied. Similarly, linear property of second term also would be satisfied. That means f of AB equal to trace of AB. This is be the bilinear form. But this is not be inner product. Why not inner product? For this, I have told you many times, to define inner product, check the positive definiteness. For this, inner product, f with itself, this is would be f of a square, and f of a square is equal to actually the trace of a square. And by the property of inner product itself means this is greater than equal to 0. And when inner product equal to 0, inner product itself with itself, that means f with itself is equal to 0, that imply f equal to 0. Notice here trace of a square equal to 0. For this, consider A equal to 0, 1, 0, 0 matrix. We all of us know this is the null matrix. So A square equal to 0, but notice here the A matrix is non-zero matrix, but square term is 0. That means inner product F with itself is equal to 0, but I have got F not equal to 0. So F of AB equal to trace of AB. This is bilinear form, but not be inner product. I hope my all viewers have understood. That means bilinear form does not imply always inner product, but inner product always imply bilinear form. So option 1 is a bilinear form but not inner product. Next, option 2, f of AB equal to trace of AB transpose. Next, f of AB equal to trace of AB transpose. At first check the bilinear form. F of A comma alpha B plus beta C. By the defined function, this is equal to trace of A alpha B plus beta C transpose. This is the by the property of inner product. The f of AB means since trace of AB transpose. Therefore, this is equal to trace of A. By the property of transpose, this is equal to alpha B plus beta C transpose means alpha B transpose plus beta C transpose. And by the property of scalar, we can write trace of A alpha B transpose means trace of alpha A B transpose. Here beta is also scalar, so we can write plus beta AC transpose. And property of the trace, we all of us know trace of alpha A equal to alpha times trace of A. Therefore, by the property of the trace, we can write this as alpha times trace of AB transpose plus beta times trace of AC transpose. And trace of AB transpose means by the defined function f of AB, and trace of AC transpose means by the defined function f of AC. Therefore, f of A comma alpha B plus beta C equal to alpha times f of AB plus beta times f of AC. Therefore, properties of linearity has satisfied. Similarly, here this is linear with respect to second component. Also, this would be linear with respect to the first component. So, this is the bilinear form. Now, check the other option. Second option of inner product is f of AB. Is this symmetric? F of AB equal to f of BA. For this, next, f of AB equal to trace of AB transpose. Now take transpose, trace of AB transpose to the power transpose. By the property of transpose, this would be, we all of us know, by the property of transpose, this would be B transpose transpose times A transpose. And B transpose transpose means obviously B, that means this is trace of BA transpose. And trace of BA transpose is nothing but trace of BA. Therefore, f of AB equal to f of BA. Symmetric property of this function has satisfied. Third, positive definite. If inner product itself, that means f of A comma A, this is equal to trace of A transpose. And trace of A transpose, notice if we consider second 2 cross 2 matrix A11 arbitrary 2 cross 2 matrix A12, A21, A22, A transpose means A11, A12, A21, A22. Therefore, this would be only trace of A transpose, this would be A11 square plus A22 square. That means f of AA, which is equal to trace of AA transpose, this is actually summation AII whole square, where I running from 1 to n. I hope my all viewers have understood that this part always would be greater than 0. And we all of us know when f of AA is equal to 0, that means this term is equal to 0 and this term is equal to 0 means component wise AII equal to 0. I hope my all viewers have understood this is. Okay. So, f of AB equal to trace of AB transpose. This is B inner product. Also be bilinear form. Similarly, f of AB equal to trace of BA transpose. Both these inner product space. I hope my all viewers have understood. That means bilinear form. This does not always imply inner product, but inner product always imply this is bilinear form. Okay? I will stop here. In my next video, I will discuss orthogonality of inner product space, orthogonal basis, orthonormal basis, this type of question. We all of us know this actually depends on inner product space. But at first, I will highly recommend you please see today's video with pay attention, because this type of question actually very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.